Our next session, it is our great honor to welcome our speaker, Mr. Ahmed Shihab, Chief Product Officer at WD. Mr. Ahmed Shihab will share his insights titled Reinventing Storage for AI at Scale. Ladies and gentlemen, please welcome Mr. Ahmed Shihab.
Good morning. Good morning. There you go. Well, thank you for making it this morning. My name is Ahmed Shihab. I am the Chief Product Officer at WD. I've spent the last 20 years or so in storage, and that storage is in companies like NetApp, AWS, and Microsoft, and now at WD. One of the things I've seen over the years is that the storage landscape and the storage stacks continuing to evolve over time. From the enterprise storage stacks to the cloud, to the scaling of the cloud, and now to AI. AI starts at a much bigger scale. So what I wanted to talk about today is really, what is the AI storage stack look like? What's in it? How does it work? Why is it important for us to understand that? But before we do that, let's just ground ourselves in what is AI? I don't have to tell the audience here who are very smart and know a lot about AI, especially with GTC today or this week, to understand that AI is really two workloads. There's training and there's inference. The training workload is where you create the models, you create the systems, and inference is how AI makes money. It's when we interact with AI, when you ask a question, when you request an API call, that's inference. And those are two very big workloads. But underneath all of that, it is all about the data. Data sits underneath all of the compute cycles, all the compute workloads. You've heard that training requires a lot of data, but inference does too. So AI is really a loop. That's very different to what we have seen before, and that requires a different way to think about storage. Because you train the model, you generate data, but you feed it back to create an agent, to improve the model so it can answer your questions better the next time. And that leads to something that's interesting. AI also has two elements to it. We've heard a lot about compute and how important it is that we have the right GPU cycles, the right CPU cycles. But what we don't talk about is the amount of data that we have to use to train those models. Those models require so much data that we have heard about. It accumulates very quickly. More data, the better the model. The more inference, that also generates data. And that data feeds back. Let's take a simple example. When a user, any one of you here in the audience, how many have used AI agents? Don't be shy. No, it's not a quiz. Right? When you use the AI agent, your data doesn't disappear between sessions. It stays there. What you asked it a week ago, it's still available to you. The data that you store isn't used by some other user. Right? If you ask about cats, you ask about birds, you don't want a different answer. Right? Two very different answers. So whereas compute cycles can be reused, the training cluster could be reused for inference. Different users who complete their inference runs can let go of those resources and somebody else can use them, but the data stays. The data continues to build up. The more you use it, there's more data. So what are those data sets? How do they build up? There are three typical workloads in AI from a data point of view. There's two compute workloads, there's training and inference, but there are three storage ones. Training, we've heard about. We've been talking about it for the last 5 years. Right? Who hasn't heard that training requires exabytes of data for processing and learning? I don't see any hands up, so I assume that's everybody's heard it. Right? Training requires vast amounts of data. It's been driving the growth in storage for quite some time. But what we talk about little less is the amount of data that inference uses. When you ask AI to do something for you, and we'll go through an example later, it actually uses an incredible amount of data to synthesize its output. But that output is also stored. And that's the bit we don't talk about very often. Generating output from inference is one of the fastest growing compounding effects of AI storage. I'll give you an example, a couple of examples. MIT study suggests that this is becoming 90% of the workload. But a personal experience, I had a customer once training an AI model to drive cars. They ran out of real-world data to train their model because they wanted to train it on specific examples. What happens in an accident? What happens if there is snow on the road? They couldn't wait for real-time data, for real-world data. So they used inference to generate the training data. And they stored that data and they trained the model. So the output from inference is something we don't talk about very much. And it's more than just the output that you seek. It also generates compliance logs, more data to train the models and refine them, and many, many other things. So that creates scale. Something we don't talk about very often. Because our intuition when we talk about storage is what we experience every day. But at this scale, now we're talking about tens, if not hundreds of exabytes of data being consumed and generated. So what does the effect of that scale? Let's take an economic look at it. Because one of the things I learned at the hyperscalers is that you've got to pay attention to scale from day one. It defines your architecture. If you don't pay attention to it, your service is unaffordable. So let's take an example here. If you change the cost for storage, any storage, by 1 cent, 1 penny per gigabyte, if you're buying a laptop, it's an extra $10 with a 1 terabyte drive. Not a big deal, right? But when you get to the exabyte and 100 exabyte scale, that's a big number. That's $1 billion difference. So you've got to pay attention to the cost of your storage at the scale that AI runs at. AI today consumes hundreds of exabytes across the world. You've seen the news reports. Certainly my personal experience says that is true. So the economics matter. Paying attention to those pennies really does matter. So how does AI do this? It has all these workloads. It has economics of scale it has to pay attention to. But it has to balance all of that with a storage stack. So what does it look like? If you pay attention to the cloud as it was, as is, everybody will tell you there is a hot data sitting on SSDs and the cooler data sitting on hard drives. Object stores, different types of file systems, all use hard drives for the majority of the data. IDC and others report 80% of the data sits on hard drives in the cloud. I can confirm that. Storage for AI, though, didn't get simpler to solve this problem because AI has different needs. It needs performance, so it can serve millions and millions of users all at the same time. It needs to understand the meaning of the data, but it also needs to store all of the data that's created. So it actually got deeper. It didn't get shallower, it didn't get simpler, it didn't become all one technology or another. It actually became something new. So at the top, you have things like the model weights and sitting in GPU memory and in the local HBM memory. You have a KV cache that expands your memory space. And you have a new layer that stores meaning called vectors and embeddings. And it actually describes what data exists in the bulk object store or the bulk file system. It describes the meaning of a file so that AI can reason over it without having to go fetch it back. So what is a vector? Anyone heard of vectors? Okay, you don't count. A vector is a thing that describes the meaning of an object, a file. Let's take this example here. This is a picture of the WD NASDAQ bell ringing event earlier this year. What do you see in this picture? You see a bunch of pixels. But the meaning of the picture is we see Irving Tan, our CEO, in the middle. We see confetti. We see a number of WD employees and the logo behind it. That's the meaning of the picture. So vectors describe that. They read the picture and they distill that meaning from it, and they store that as mathematical representations called vectors. The picture is several megabytes stored on hard drives. The vector that describes the meaning is a kilobyte. You can store that on flash quite effectively. And when AI wants to reason about something, it really wants to reason about the meaning of something. That's why it's an important new addition, a new layer and a new tier that's associated with AI storage. Let's best illustrate this with an example. Preparation for this meeting, everyone here. I asked AI to do two things for me. I won't say which one. But I asked it to create a simple video. 8 seconds, no bigger than 4 megabytes, that describes a scene where a barista in a cafe hands over a coffee to a customer and then shows them the bill. Quite simple. At the same time, we asked it to tell us what was happening in the background, what data it was reading, and what it was doing at the same time. AI turns out to be useful like that. It can tell you what it's doing. It can reason about it. I don't have to ask any engineers to do it for me. So the first thing I did was it tried to understand what I was doing. What is the intent of the question of the prompt I was asking it to do? So it went into its memory, it fetched the models, it fetched the semantic decoder, and started to decode it. It fetched about 2 gigabytes of data just to understand what I was asking. By the way, that happens every time you ask a question, or every time there's an API interaction with an AI, or an agent is doing something on your behalf. That's the start of it. Then it went off and read another 40 gigabytes of data to understand what is a cafe? What does it look like? What does the lighting look like? What does a human look like? How does paper behave? It went and fetched all of those things. It also understood that it needed to put the data or the writing on the receipt in English, because it knew I spoke English. Right? So it went and fetched all this data. It fetched 40 gigabytes of data from both the deep store on hard drives, from the vector databases, and put them in the cache, and then pulled them into memory. That's a lot of data to read. And the way it did that is by understanding the intent, go into the vectors, and then fetching all that information. Then it started to generate output. Did I miss that? There we go. Then it started to generate the output. It created about 4 gigabytes of data. Don't forget, this is an 8-second video. But the amount of data it read and it created, so far we're up to 46 gigabytes. Some of it is being stored back on the bulk tier, some of it is stored back onto the vectors, some of it is stored back on the KV caches. Right. And finally, it generated the output. It took all those intermediate steps, it understood what I had to do, it created the sound, and then it put it together and gave me the output. That's what it looks like. Pretty cool. 8 seconds. 4 megabytes of data that was created, but to generate that 4 megabyte file with 8 seconds of video play, we read 40 gigabytes in GPU memory. We actually generated 506 megabytes of data that is stored in the backend. All that for the 4 megabyte file I wanted. So you can see how the data is building up so quickly. This is a simple example. You can almost say it's a trivial example. I know that in our company that we will spend petabytes of data to do scientific research, to design hard drives, to design our logistics, to understand our business patterns. All that data gets compounded. All those scenarios get built up. And I have a confession to make. It looks nice and neat the way we did this, but it actually took 7 attempts to do this. It wasn't quite the right cafe. It wasn't quite the right lighting. So we had to go back several times. Those are the iterations and versions. So instead of 46 gigabytes of data, it was actually 320 just to produce that 8-second video that you saw. Now imagine this compounding over billions of transactions. Imagine that the limit is really your ingenuity, what you want to do, what you can imagine you can do with this tool. That's pretty staggering. That data continues to compound, continues to build up. That cycle begins to build up. So the inference output doesn't disappear. As well as the data that I want to use or you want to use, there's also intermediate data like logs, compliance records, all sorts of things that inference has to keep, either by legislation or it's useful for us to handle over time to make the models better. If you're creating an agent, you feed that back into training. You're creating a virtuous circle. Data continues to build up. And it builds up in the bulk hard drive tier. That is very different to our experience with enterprise systems. It's very different to our experience with using the cloud. In the past, if you put a video or a photo in the cloud, it didn't generate any more data. It didn't generate new photos for you. AI can. And that's very different. That's a structural change in the effects that compound data growth. So what does that mean to the stack? I'm often asked is, what happens here if, where does all this data live? Does it live on flash? Does it live on hard drives? Does it live on something else? The reality of it is the AI engineers or the storage engineers being very clever about this. They use the best technology for the best intent it's capable of. Hard drives continue to be the bulk storage. Lowest cost, great for doing sequential reads and writes, very large data accesses. Oops. Flash is very good at reading small data systems or data fragments, like vectors. It's also very good at cache, because it's very fast, and it's very good at reads. And that hot data, and then you get into the GPU memory or the CPU memory after that. So the stack is different. It's very different to what we see in the traditional cloud environment, where you just have two tiers. But none of those are wasted. They're necessary. So this architecture didn't happen by accident. It happens because of economics. I'm often asked the other question, which is, won't Flash take over everything? And that's typically when I show them this. These aren't my numbers. We got this from an online tool. You can see the reference. If you were to choose all Flash data systems for everything versus all hard drive systems for everything, this is based on public pricing. There's nothing I'm revealing here that's new. The difference between all Flash and all hard drive at 200 exabytes, which, by the way, is about the publicly acknowledged size of something like S3 in Amazon, it's $96 billion. Put it in different terms, that's about 3 million GPUs. So if you were to choose things based on technology, not economics, and the architecture done that way, you could have 2 million less GPUs, those GPUs that you could use to expand your business. So you're choosing the right architecture, the right balance, and typically it's 80-20 of flash, 20% flash to 80% hard drives, gets us the optimal point, and then you have more capital to invest in more GPUs that serves more users, that serves more storage. And that doesn't stop there. IDC is forecasting that between now and the end of the decade, there are 300 zettabytes of additional storage that's going to be driven by AI, created. Now, that's zettabytes. That's 300,000 exabytes. Let's say IDC is wrong by a factor of 100. It's still 3,000 exabytes. That's $66 billion of hard drives, or $1.5 trillion of flash, if you go pure. That's not a good economic investment. That's why what we see in the stack is that it remains designed like this. You use the best technology where it's most relevant. Top of the stack is memory and HBM. The cache is flash. And so is the embeddings, because there are small reads and small writes, and it's all about fast access. It's great use of the technology. It's a great place for flash to earn its place. Hard drives are used for what they're very, very good at: large sequential I/O, big bulk storage, lower cost, power efficiency. And the interesting thing about this is that both the flash embeddings layer that holds the meaning of the data that is in the bulk storage and the bulk storage layer, they grow together. The more bulk storage, the more embeddings. The more embeddings, the better the AI. The better the AI, the more data. And the cycle continues. This is why I believe that the storage stack is elegant. It's pragmatic. It's been designed with the economics of scale in mind. It's not about technology. It's not about brand loyalty. It's about what's practical and what makes sense. If you go one way or the other, AI could be too slow, or it could be too expensive for any of us to afford it. It will hamper its adoption. It's a very elegant answer. So I hope this has been thought-provoking for everybody here. I know I threw a lot of things at you in a very short amount of time. But it's an exciting subject. It's driving innovation in the industry. It's driving flash to do better endurance and better capacities. It's driving the hard drive industry to deliver more performance, more capacity. Because we all need AI to be successful. Not because it is a technology that we like, it is beginning to drive economic output for all of us. Companies that adopt AI are doing better. So it's become a reality and a necessity for all of us to adopt. And this is why it all sits on data. Without your data, without the data that sits in the systems, AI can only do so much. And that data continues to grow and grow and grow over time, alongside compute. So thank you. Thank you for your attention. I appreciate your time today.
感谢 Ahmed Shihab 先生精彩的分享。下一个精彩场次 ，AI 资料中心的电力挑战与解方，即将在不久后开始。